are chemical equations giving you a tough time? Don't worry, you are in exactly the right place. In the next few minutes, we're going to break down everything you need to know about chemical reactions and equations so you can absolutely ace your board exams.
So here's our game plan for today. First, we'll get a really solid grip on what a chemical reaction even is. Then, we'll learn to speak the language of chemistry, the symbols and formulas. After that, we'll tackle the most important skill, balancing those equations. We'll put it all into practice with some real, star-marked exam questions. And finally, we'll do a quick-fire round to make sure all these ideas are locked in your brain. Ready? Let's do this. So, what's the big deal with chemical reactions anyway? Well, they are happening literally everywhere all the time. Think about a nail rusting outside, or even the food you're digesting right now. These are permanent changes, and we're about to find out exactly what's going on behind the scenes. Okay, let's make this super simple. Imagine you have a piece of paper. If you fold it into an airplane, it's still paper, right? That's just a physical change. But what if you burn it? Well, you get ash and smoke. You can't get that paper back. That, my friends, is a chemical change. A completely new substance has been formed.
So at the very heart of every single chemical reaction is this incredible dance of atoms. Old bonds between atoms break, they rearrange, and new bonds form. It's like they're all swapping partners at a dance. And the result? Something totally new, with its own unique properties. Every chemical story has its characters, right? You've got a before and an after. The before ingredients, the stuff you start with, are called reactants, or abicatic. And the after results, what's been created at the end, those are the products, or wood bud. See? Simple as that. Okay, so how do scientists from all over the world talk about these reactions without getting confused? Well, they use a kind of secret code, a universal language that lets them communicate with any chemist anywhere. Let's learn how to crack it. Now, the first way you could write a reaction is just with words, a word equation. It's kind of like writing a sentence that just describes what's happening. It's a great starting point for sure, but as you can see, it's a bit of a mouthful. And chemists, well, they're all about being efficient. So they came up with a much smarter way. And this is where the real magic happens. By replacing all those words with chemical formulas, we get a chemical equation. Just look at how much cleaner and shorter that is. It tells us not just what's reacting, but the exact recipe, how many atoms of each element are involved in this whole dance. But wait, we can add even more detail. These little symbols in the parentheses, they're like status updates for each substance. S is for solid, L is for liquid, G is for gas, and AQ is for aqueous, which is just a fancy way of saying it's dissolved in water. We can even show if a reaction needs a little push from heat, or maybe a helping hand from a catalyst, which is something that speeds things up without getting used up itself. All right, let's talk about the one thing that can trip up so many students, balancing equations. But here's the secret. It's not just some random rule your teacher made up to make your life harder. Nope, it's based on one of the most fundamental laws of the entire universe. It's called the law of conservation of mass. And really, it's pretty simple. You can't create or destroy matter. You can't just make atoms appear out of thin air or make them vanish. Think of it like playing with Legos. You can take apart a Lego car and use those same bricks to build a house, but you'll still have the exact same number of Lego bricks you started with. Atoms work the same way. And hey, don't just take my word for it. Look at this. Here's the proof in action. Look closely at that scale. The mass of the reactants before the reaction is 300.23 grams. And after the reaction is all done, the mass of the products is exactly the same, 300.23 grams. Not a single tiny bit lost. That's the law in action. So, how do we make sure our equations obey this law? We balance them. It's like solving a little puzzle. And here's your 5-step strategy. First, just write the equation. Then, do a head count of atoms on both sides. Now, here's a pro tip. Always start with the biggest, most complicated-looking compound first. It usually makes everything else fall into place. Then, balance the rest. And finally, and don't skip this, always do a final check to make sure it all adds up. All right, theory time is over. Let's see what you've learned. We're going to tackle some real exam-style questions now. This is where the rubber meets the road. So pay close attention, because I can almost guarantee you'll see questions just like these on your exam. Here we go, a typical star-marked question. They give you their reaction in words, and your job is to translate it into the language of chemistry. Now, the first and most critical step is to write those chemical formulas correctly. Take a second, you've got this. And here's the solution.
So let's do a quick atom count together. On the left side, the reactants, we have 2 hydrogen atoms and 2 chlorine atoms, right? But on the right side, the products, the original HCl, only has 1 of each. So what do? We simply place a big 2 in front of the HCl, and just like that, everything is perfectly balanced.
Here's another curveball they might throw at you. The equation is already balanced for you, but it's missing those state symbols. So your mission, should you choose to accept it, is to figure out if these substances are solids, liquids, or gases. And here we have it. Sulfur dioxide and hydrogen sulfide, well, they're gases, so they each get a little G. The sulfur that forms in this reaction is actually a solid that settles out, so it gets an us. And of course, the water that's produced is a liquid, so it gets an L. Make sense, right? You are doing great. Now, to make sure all this information really sticks in your brain for the exam, let's do a quick-fire review round. Let's see what you remember. Okay, first up, let's start with a concept you probably learned in previous classes: valency. What does it actually mean? What is that number telling us? Yep, if you are thinking it's the combining power of an element, you absolutely nailed it. Think of it like this. Every atom wants to have a full outer shell of electrons to be stable and happy. Valency just tells us how many electrons an atom needs to give away, take, or share to get to that happy place. It's the driving force behind all of chemistry. All right, use your brain power for this one. I want you to imagine dissolving some sugar in water. Got it? Now imagine a nail that's been left out in the rain and is all rusty. Both are changes for sure, but what's the fundamental difference between them? The answer really comes down to whether or not you can reverse it easily. With the sugar water, you could just evaporate the water and get your sugar crystals back. No new substance was made. It's a physical change. But with the rust, you've created a totally new substance, iron oxide. You can't just unrust the nail. A chemical reaction is a one-way street. And that's it. You now have the toolkit, the secret code to unlock the chemical secrets of the universe. From the battery powering your phone to the air you're breathing right now, it's all about chemical reactions. So go out there, keep practicing, and start decoding the amazing world around you. You've got this.